All right, well, welcome to our lecture recording for section 7.1. We're starting on a new chapter, new topic. Um, this chapter is kind of a mixture of topics, but the theme is to learn more about ways to describe mathematical curves, so that we can do more calculus with them. This chapter is kind of a nice little way to tie up um, these 2 semesters of single variable calculus that we've been studying in Calculus 1 and Calculus 2. And it's also a nice introduction to multivariable calculus for those of you who are moving on to Calc 3. We won't be doing any multivariable calculus in this chapter, but the things we're going to be learning about are things that are relied on quite a bit in Calc 3. So this is a nice place to kind of tie off the course, and it's a nice little change of pace. We've been doing something very analytic that wasn't very visual, and now we're going to do something that's kind of more the opposite. A little more visual, more of an emphasis on graphing. Alright, well, let us go ahead and have a look at our outline for section 7.1. Alright, so sometimes when we give a mathematical description of a curve, the shape of the curve isn't the only thing that matters. Okay, sometimes the order and speed at which the points on the curve are plotted are just as important. Okay, in particular, if the curve is the path of a moving object, then not just the shape of the path matters, but which way the object was going and how fast it was going. Those are often important as well. So that will give us a little bit of context. Okay, now there's also other uses for what we're going to do that don't really have anything to do with moving objects, but that's kind of a nice framework to begin with. So in particular, I'm going to motivate what we're doing in this section using an example that involves a moving object constructing a curve for us. Okay, so let's imagine a CNC machine. This is the sort of thing that you would see in a factory. Okay, a factory making machined metal parts. And let's say the CNC machine is being programmed to cut a groove in a plate of aluminum. Pretty basic task. Okay, maybe it's making letters, or maybe it's making a groove that something fits into. Okay, it might be using a router, or it might be using some type of milling attachment. Okay, not real important for the sake of our mathematical example, but it's that kind of thing we're talking about. So the machine tracks the position of the cutting tool using rectangular XY coordinates, okay, which is actually pretty typical for machines and machine shops. They tend to track the positions of cutting heads using actually X, Y, and Z coordinates, but the Z is that third dimension that we won't really worry about just now. We're going to think in terms of 2 dimensions. And we're going to assume everything's measured in inches. And we're going to program the machine to do a fairly straightforward task. Okay, we want it to cut a groove in a straight line from the point 4, 3 to the point 8, 0. Okay. Now, I'm going to begin with something that I think we're all pretty familiar with, which is just constructing an equation of the line connecting these 2 points. So we'll call that a standard rectangular equation. We don't usually bother being so specific about what we mean. Rectangular means we're going to use XY coordinates. Standard means we're going to do what we've been doing for most of the last 2 semesters and the courses before that, which is constructing functions where the variables are x and y. Okay, but the reason I need to start making this distinction is because we're going to talk about different ways to construct rectangular equations, and even equations that are not rectangular eventually in this chapter. So anyway, we're just going to do a standard y equals mx plus b type of equation for this line, and we'll use that as our starting point. Okay, and we'll also be specific about the domain. Okay, so let me flip my view over. Alright, so here's what we were just discussing. So we're gonna cut a groove from the point 4, 3 to the point 8, 0. Now there's actually some directionality to this. Okay, we're going to cut it from left to right. Okay, so in many contexts we don't really bother thinking about a direction to how we're moving through the path of a curve. But in this context, we're talking specifically about starting here and going there. So we would say actually that this curve has an orientation to it, and that actually kind of matters in this context. So we'll look at a formal definition of that a little later. For now, let's just build the equation of this line. Okay, in order to do that, we need a slope and a y-intercept. For the slope, we know slope is just rise over run. And in this case, our rise is actually negative. We're dropping 3 and going over 4. So now we can say y equals negative 3/4 x plus b. We need a value for b in order to complete our equation. To get that value, we can just choose either of our known points and plug them in. So maybe I'll just take this one since it's still on the screen. X value, y value. So I'll put 0 in for y. And negative 3/4 times 8. Well, negative 3/4 times 8 is negative 6. So it looks like 0 equals negative 6 plus b. So 6 equals b. And therefore we can say that y equals negative 3/4 x plus 6. Now that's the equation, but technically that equation would be the description of not just this little line segment, but an entire infinitely long line. But in this context, we know we're talking just about this line segment. We probably don't want the machine to keep cutting once it gets to 8,0. We want it to stop, and maybe that's all there is to do, or maybe it needs to turn and go in another direction. But 8,0 is clearly our stopping point, and 4,3 is clearly our beginning point. So there's a domain restriction. Now if I want to indicate that a function has a domain restriction, I can just put a comma after the function and write it in. 4 is less than or equal to x, and x is less than or equal to 8. So that's our answer for part A. Okay, but now let's come at this a little different way. Okay, when I describe it like this, I can now tell the machine the path to take, but I might also need to tell the machine how fast it should be moving through that path. Okay, and here's where the alternative representation that we're going to introduce in this section really starts to make a difference. So, moving on to part B, let's look back at our outline. Okay, part B. If the maximum speed for the cutting tool is 1 inch per second, how long should it take to make this cut? Okay, well it makes sense that there's probably some maximum speed we should go when we're cutting through this aluminum. If we go too fast, we might not make a very good cut. Obviously we don't want to go slower than we have to. We're manufacturing, time is money. Okay, so let's think about this again. We're supposed to go 1 inch per second. We're going down 3 and over 4. So if I apply the Pythagorean theorem, I can say that the length of this side is the square root of 3 squared plus 4 squared, and that simplifies to 5. So if I want to go 1 inch per second and I'm covering a distance of 5 inches, then I guess I better take 5 seconds to make this cut. So that's my answer for part B. Okay, 5 seconds for us there. Now part C. Construct a linear function, so one similar to what we just did, but this time instead of having x as the input and y as the output, we're going to have t as the input, t for time in this case, and x as the output. Okay, and we're going to have it so that we want x to go from x equals 4 to x equals 8 as t goes from 0 to the time we just computed in part B. So x goes from 4 to 8 as t goes from 0 to 5. All right. Alright, so when t is 0, we want x to be 4. Okay, this corresponds to when we're just starting to make the cut. And we don't want x to reach 8, the other end of the cut, until t is at 5. So that gives me two ordered pairs. Okay, 0, 4, and 5, 8. And I can use them to build a function similar to the one I had before, only this time instead of y equals mx plus b, it'll be x equals mt plus b. T will be the input variable, x will be the output variable. The slope will still be the rise in the output variable. So if I go from 4 to 8, that's a rise of 4 and a run of 5. So m is 4/5. So that means x equals 4/5 t plus b. And then I can take either of my ordered pairs and plug them in. So I could say, alright, 4 equals 4/5 times 0 plus b. Alright, so b is 4. And that means that my answer here is going to be x equals 4/5 t plus 4. So what I have now is I have a description of the x-coordinate as a function of time. So presumably this machine will track both the x and y coordinates as it moves the cutting head, and I've now given it a formula to tell it where it should have the cutting head horizontally at each particular time. Oh, but we need to put in our domain restriction to be finished with this problem. We want t to be from 0 to 5. Now, I need to do the same thing for y. Okay, need to do the same thing for y. I want y to go from 3 to 0 as time goes from 0 to 5. Now, I could do this directly by setting up two more ordered pairs. Pairs that pair time values with y values. But since I already know, well, you know what? Let's go ahead and do it directly, and then we'll do a comparison later. And I'll kind of make the point I was just starting to make at a later time. So let's actually do it that way. Let's make ordered pairs of time with y. So when t is 0, we want y to start at 3, and after 5 seconds we want y to have dropped down to 0. Okay, so that means my slope would be, well, y drops, so that's negative 3/5. Okay, so y equals negative 3/5 t plus b. And then, well, actually in this case I know that my b value must be 3 because I know my y-intercept. Okay, if I put in 0 for t, yeah, y would be 3. Okay, so b must be 3. Okay, y has a negative slope because y is decreasing over the course of time. And again, my domain here is that t must go from 0 to 5. Alright, that was part D of our outline. Let's have another look at our outline to see where we're at. Okay, did part C, did part D. Alright, looks like now we've reached the point in time where we're going to go into Desmos and we're going to do some feasibility checks. Okay, we're going to see if it looks like we've done everything correctly. Alright, let's go ahead and do that. Alright, so if I want to plot a point in Desmos, it's pretty straightforward. I just type in the point. So here's where my groove is supposed to start, and here's where my groove is supposed to end. And then let's do a variable point. Okay, I'll do a point where instead of giving it an x value, I'm going to give it my formula for x. So let's look back at that real quick. Okay, here's my formula for x. X is a function of time. And here's my formula for y. So instead of putting in x and y values, I'm going to put in these two formulas. And they should generate all the x and y values that I need on this little line segment. Let's see if it works. Alright, so my x was 4 over 5 t plus 4, comma, and then my y was negative 3 over 5 t plus 3. Now it's asking me to fill in the domain here. I'm going to tell it t needs to go from 0 to 5, and when I do that, it does look like I get exactly the line segment that I want. Okay. Now I can see just at a glance that if I plug in 0 for the t's, then what's left behind here is 4, 3. So I can see it's starting in the right place, and therefore it's probably ending in the right place. But let me make a little animation here. I'll make this little animation by changing t over to a variable that Desmos will recognize as something we could do a slider for. And I'll tell it I want that slider, since k is really time here, I want that slider to go from 0 to 5, and I want it to go in really small steps, so we'll say like 0.1. Yeah. So now I can, if I tell it to animate, I can watch my little animation of my cutting tool cutting out my groove. Now, of course, I don't want the cutting tool to come back, but for the first 5 seconds of the animation, looked pretty good. Exactly what we were looking for. All right. Well, let's go back to our outline and see what else there is to discuss. Oh yes, I said that I would circle back and show that the equations found in parts C and D can be combined to give the equation in part A. Yeah, that's a nice way to tie this little problem up here. Yeah, I just realized I don't think you saw what I was doing in Desmos there. I forgot to put my display capture back on. There we go. Alright, well now you can see what I was doing. Okay, all I did was I took my parameterization here, where I entered in the formula for x and the formula for y. Okay, I copied it down, so I cut and pasted it, and I changed t to k just because k is something that Desmos will let me put in a slider for. And I just made the slider so that it goes from k equals 0 to k equals 5, so that if I drag our way through the slider, we can see our cutting head going through this groove over the course of 5 seconds. Alright. Alright, so here's our equation for x, here's our equation for y, and then way up here was our original equation relating x and y. Okay, if we've done everything correctly, and I think we have, since the graph looked right in Desmos, it should be the case that these two equations together are equivalent to that original equation. And I can see that by choosing either one of them and solving for t, because if I solve for t, I can then plug into the other one. So let's start with this one here. X equals 4/5 t plus 4. And I'll go ahead and jot down that y was negative 3/5 t plus 3. Alright, if I want to solve this for t, then I need to move the 4 over here. So x minus 4 equals 4/5 t. And I need to multiply by the reciprocal of 4/5. So that would be 5/4 times x minus 4 equals t. And now I know what to plug in up here for t. So when I plug in 5/4 times x minus 4, I get y equals negative 3/5 times 5/4 times x minus 4 plus 3. Well, let me see. I can see those 5's canceling, and then a negative 3/4 would come through here, and I would get y equals negative 3/4 x. Negative 3/4 times negative 4 would be plus 3, but then there was also another plus 3. So I have y equals negative 3/4 x plus 6. And that is where we started. That was what we called our standard rectangular equation. Okay, basically the type of equation you guys have been studying since Algebra 1. Our standard rectangular equation for this line. Okay, these two equations together are an example of the topic of this section, which is parametric rectangular equations. They're still rectangular because they still use the rectangular xy coordinates, but instead of having one equation where x is the input variable and y is dependent on x, we've split it into two equations where x and y are both dependent on a third variable, which in this case represents time. Okay, and for purposes of programming this machine, this is actually a little better way because it allows us to control how fast our cutting head is moving in a more direct manner. Okay, these are what we would call parametric equations. Okay, so I think at this point in time, we want to go ahead and have a look at a formal definition in the book. Okay, so here we are on page 607, okay, near the beginning of section 7.1. Okay, and it says, if x and y are continuous functions of t on an interval I, then the equations where x is some formula involving t and y equals some formula involving t are called parametric equations, and t is called the parameter. Okay, a parameter is basically just a variable that has multiple other variables depending on it. Okay, which is kind of how we use that word in everyday conversation. Parameters are things that determine other things. Okay, in a loose sense. Now, this definition continues on. It says the points x, y that are obtained as t varies over the interval I is called the graph of the parametric equations. Okay, it's basically the same thing as the graph you would get if you combine those parametric equations into one standard equation with just x and y. Okay, you're still getting the same ordered pairs, you're just generating them a slightly different way. The graph of the parametric equation is called a parametric curve. A lot of times a C is used for that. You'll certainly see that a lot if you move on to Calc 3, that notation of capital C for a curve. There's one other thing I wanted to point out here at the bottom of page 608. Okay, it says the arrows on the graph indicate the orientation of the graph, that is, the direction that the point moves as t increases. Okay, so where's the graph they're referring to? Here's the one in the book. So you can see as time moves forward, the points are moving from this point up to that point, so the arrows are drawn on the curve to show that orientation. Now the thing about describing a curve parametrically is that it gives you control to reverse the orientation, so you could make the points flow the other way as time moves forward, okay, which would represent something going backwards through the groove, which would be perfectly reasonable. If you can go one way on a path, you can usually go the other. It also gives us control over things like how fast it's moving and where it's starting from. So let's talk about that a little bit. Sketch the parametric curve from the previous example showing its orientation. Well, we did that. Okay, we did already sketch that. But now let's move on to this. Let's create a new parameterization of that same line segment. Okay, but this time we want our parameterization to start at the point 80 when t is 0 and end at 4, 3 when t equals 10. Sketch the curve and show its orientation. Okay. Well, it just got dark outside. I think I'm going to have to flick a light on. Yeah, it's actually getting a little dark on my page here. Well, let me turn the light on. Alright, well, I now know why it suddenly got dark. Check this out. See if you can see this. It's snowing outside on tax day, April 15th. Crazy and kind of fun. Alright, so we were going to rebuild our parameterization, but this time we were going to make it so that we started at the point 8, 0 and ended at 4, 3. So I'll remake my ordered pairs, t and x. So I want x to start at 8 and end at 4. And remember, we said we want to go slower this time. Maybe we're making a deeper cut or something. So we want to take 10 seconds instead of 5 seconds. Okay, so this time it looks like my slope would be, my output variable is dropping, so that's my rise. My rise is negative. Run is still positive. So -4/10 or -2/5. Okay. Need to refocus my camera there. So that would be x equals -2/5 t. And I can go ahead and put in +8 because I can see that when t is 0, x would have to be 8. Okay. Now, I could build y from scratch, or I could just make use of the fact that I already know that x and y have to satisfy this equation. This is that first equation we built, the standard rectangular equation. Since x and y have to satisfy this equation, now that I know how to parameterize x, I could just plug that in to parameterize y. So I think maybe for the sake of variety I'll do that this time. So y equals a broken pencil lead, -3/4 times -2/5, not x, t. Alright, so that's a t +8. And then, let me see, we still have this +6 back here. So then y equals, well, let me see here. 2 and 4 could cancel. Those would cancel. All right, so that would be 3/10 t. Y is 3/10 t. Yeah, but that negative 3/4 still has to distribute to the 8, so that would be, well, that'd be minus 6 plus 6. Alright, so it looks like my parametric equations are x equals negative 2/5 t plus 8, and y equals 3/10 t. Now let me just check. When t is 0, x would be 8 and y would be 0. That's right, we want to start at the point 8, 0. And then after 10 seconds, we want to be at the point 4, 3. So if I put in 10 for t, I'd get negative 4 plus 8 is 4, and 3. Alright, so that looks right. Now let's just kind of check ourselves real quick. Desmos can help us out here. Alright, so to enter my parametric equations in Desmos, I basically just have to act like I'm putting in a point, and I put in the equation for x. So here we go, equation for x, and then the equation for t. It's actually kind of nice that Desmos is like this, because this is the format we use a lot later on when we get into talking about vector valued functions in Calc 3. Now you notice it didn't draw the whole line segment. Whenever I do parametric equations, Desmos defaults to a t range of 0 to 1, but we want a t range of 0 to 10. That'll get us all the way there. Okay, so let me see, did we do everything that the problem called for? Sketch the curve and show its orientation. Okay, well, let's do that. The sketch will look pretty similar to how it looked before, but with one important difference. 1, 2, 3, 4. So 4, 3 is right there. 5, 6, 7, 8. Okay, the key difference will be this time, when we draw our sketch, we'll put on a little arrowhead on the curve showing that the orientation is now right to left. And on top of that, it's a lot slower. We've slowed down our cutting tool for whatever reason that we need it to. Okay. So, a few points to make here. In general, we could create an unlimited different sets of parametric equations for a given curve, okay, or for a portion of a curve, depending on where we want to start, which way we want to go, and how fast we want to go. Okay. Now, we haven't discussed this yet, so this is worth mentioning. Okay. We constructed our parameterizations basically from scratch by looking at the relationship between each variable with t, each of the dependent variables. Okay. However, a lot of times we're going to build a parameterization by starting with a standard equation. If nothing else, a lot of times we'll start with that just because those are the equations we're most familiar with and are most likely to know how to build from scratch. Well, if you already have a standard equation, one way to construct a parameterization is to set the input variable equal to the parameter. So basically, just like say x equals t, and then replace the input variable with the parameter in the equation of the function to get the other equation. Okay, that's even simpler than it sounded. It took a lot of words to say something pretty simple. So, here's a curve. Okay, a curve described by y equals x squared plus 1. Okay, that's a parabola. Okay, we've already been given a standard equation for it. So, if we want to find a parameterization, and we don't necessarily have anything in mind about what that about what point we want to start at or how fast we want to go or anything like that. We just want to get some parameterization. Here's an easy way to do that. Let me flip this piece of paper over here and get these pieces of paper out of the way. Yeah. Uh-huh. So we had y equals x squared plus 1. Part A, find a simple parameterization. Here it is. X equals t, and then, since we already know that y equals x squared plus 1, if x is t, that pretty much forces y to be t squared plus 1. In general, whatever you're going to do with x, if you're parameterizing a function where you know the relationship between x and t, generally, after you decide what you're doing with x, you're going to plug that into the standard equation to get the other parametric equation for y. Okay, and that'll kind of ensure that the two things together would be equivalent to the standard equation. Okay, now I don't have to do that. That's just a simple choice, but it's not always the best choice. Okay, I could make a different choice. Here, if I do this, then when t is 0, x will be 0. But maybe I want x to start at some other value. Like in this case, x being 0 starts me on the vertex of this parabola. Okay, maybe I want to start over on the side somewhere. So maybe I want to start when t is 0, maybe I want x to be negative 3. So I could do something like this. I could say, hey, let x be t minus 3. Okay, that would force it so that when t is 0, x is negative 3. Okay, as long as I then take that and plug it into here to get my other parametric equation, I should still get a set of parametric equations for this same parabolic curve. So y equals, well, let me see, instead of x squared, I would have t minus 3 squared plus 1. Now I could simplify that, but I don't have to. Let's check that out with Desmos real quick. So clicky, clicky, clicky. Alright, so here's the standard equation that we started with. Y equals x squared plus 1. It's in blue. And here's that first parameterization I had. X, well, let me see. The x coordinate needs to be t, and the y coordinate needs to be t squared plus 1. Okay. Now I can see from looking over here that it's going to be graphing this in green. Notice that it only graphed from x equals 0 over to x equals 1 because t is restricted to 0 to 1. But if I stretch that out and say, hey, let's let t go from negative 4 to 4, now the green covers up all of the original curve, all that was on the screen. Okay. Now let's have a look at this other parameterization. The one we did in part B where we said, hey, let's let x be t minus 3, and then y has got to be t minus 3 squared and plus 1. So notice it's graphing that in purple, and it just graphed a little bit over here because it's just graphing from t equals 0 to t equals 1, but that means it's starting at x equals negative 3. Now, if I stretch it over a ways, let's say I stretch it over to 6, now we're pretty much going to cover up everything that's on the screen. So I can create, you could see, as you can see, I could pick any starting point on the parabola I wanted, and therefore there's really an infinite number of parameterizations of this parabola, but I would construct pretty much all of them the same way. I would figure out how I want to parameterize x, and then I would plug that into this formula up here to make sure that x and y together would be equivalent to y equals x squared plus 1. Okay. Now there was a part C. Sketch the graph of the parametric equations in part B by choosing values of t to generate ordered pairs. Show the orientation of the graph. Okay, yeah, I thought this would be a good idea to do at least once. Just to one time kind of walk through the mechanics of how a set of parametric equations actually generate ordered pairs. So I'm going to set up a little table here where I'm going to pick values of t, and then for each value of t that I pick, these formulae here will fill in ordered pairs for x and y. So we'll just let t go from -3 to +3 in increments of 1. Well, that's just kind of a hinky looking 2 there. Let's fix that. Alright, so when t is -3, when t is -3, x would be -6, and y would be, -6 squared is 36 plus 1, it'd be 37. Alright, now when x is negative, or when t is -2, x would be -5, and y would be -5 squared plus 1 is 26. And then likewise, when t is -1, x would be -4, y would be 17. When t is 0, x would be -3, y would be 10. When t is 1, x would be -2, y would be 5. Okay, all we're doing is we're just generating the ordered pairs that make up that parabola we were just graphing. And let me see, when t is 2, we'd get -1 and 2. And then finally 0 and 1. Okay, if we kept going, all of this stuff is on the left side of the parabola. But if we kept going, we would generate the other side. Alright, that was part C. Let's go back to our outline and see what other interesting things there are to discuss. Okay, so we were just talking about how you can easily take a standard equation and make it into a parametric equation, a set of parametric equations. Just let x be t and then replace x with t in the equation for y. Boom, you've got your two equations. Or let x be something else. Okay, but it's also easy to go the other way. If you start out with a set of parametric equations, we've already shown an example of this. You can turn those two parametric equations into one standard equation by solving one equation for the parameter, so what we've been using t for, and then substituting into the other equation. By the way, you don't have to use t for the parameter. T is just a common choice because t, often the parameter represents time, but not always. And there is one other letter that's often used for parameters, and we'll bring that up when we get to it. Little note here, we do have to be mindful of maintaining domain restrictions and also not accidentally imposing new ones. Alright, so I think I want to actually do some examples from the book here. Alright, so here's problem number 32 in the textbook. So this is at the end of section 7.1. Notice the problem gives us a pair of parametric equations, x equals 4t plus 3, y equals 16t squared minus 9. And if I scroll up, I can see that the instructions are: convert the parametric equations of a curve into rectangular form. No sketch is necessary for this problem. And state the domain. Okay. Alright, well, let's do that. Alright, so there's our parametric equations. The book said convert it into rectangular form. That's not the greatest wording because these parametric equations are already in rectangular form. Okay. Because they're using rectangular coordinates x and y. what the book means is convert them into a standard equation that just has x and y. So this is really just a little algebra exercise. I'm going to take one equation and solve for t. In principle, it doesn't really matter which one, okay, but in this case I can see it would actually be better to solve the first one for t, because if I solve this equation for t, I'm going to have to take a square root, and that would restrict my domain, and I don't want to add a domain restriction, so I'm going to try to avoid taking square roots. So I'm going to solve this one for t, but in principle it could go either way. Alright, so it looks like if I take x and subtract 3 and divide all that by 4, that would be equal to t. So that stuff is what needs to go in right here. So y equals 16 times x minus 3 over 4 squared minus 9. Now at this point I've actually done what the problem asked for. I started out with two parametric equations, and now I've got a standard equation. Okay. Naturally I'm going to simplify it, but I have actually done what was asked. Alright, so let me see here. Y equals 16 times x minus 3 squared. Powers can distribute over division, so I can square that 4 and make that a 16. And that's nice because that gives me some cancellation. And then let me see, I've got y equals x minus 3 squared is x squared minus 6x. And it would be plus 9, but I see that's going to cancel with that minus 9. So I think I'll just stop right there and say that's my answer. Oh, but let me see. Are there any domain restrictions? Well, to answer that, I really have to go back and say, hey, did this parametric equation for x impose any restrictions on x? And it really doesn't. This is a linear equation. Okay, it's a linear equation with a vertical intercept of 3 and a slope of 4. Linear equations generally have a range of all real numbers, except horizontal ones, but we know it's not horizontal because it's not just a constant. So the range would be all values of x, which means that this equation does not have any restrictions on its domain, because x is the input variable here. So actually, if I just write nothing more, I'm good. Okay, although I think the problem did want me to explicitly say, yeah, state the domain. Okay, usually if we don't write anything, then the domain is understood to be all real numbers, or whatever it would be if there were no whatever it would be based on things like square roots in the equation. But since the problem specifically asks us to state the domain, we'll go ahead and say that the domain is negative infinity to infinity. So that's part of our answer too. Alright, well, let me see. I think the outline called for us to do another problem. Problem 17. Aha. Looks like I gotta scroll a little bit there. Alright, so in problem 17, we're given a set of parametric equations. X equals e to the t, y equals e to the 2t, and what does it say here? It says, for the following exercises, sketch the parametric equations by eliminating the parameter. Indicate any asymptotes of the graph. Alright, well, so what they're saying is rather than using t to generate ordered pairs, convert this to a standard equation. That's what they mean by eliminating the parameter. Okay, make it so that we just have one equation with x and y and no t's. And ideally then, once we've done that, we should immediately recognize what this looks like. At least that's what they're implying. Alright, well, one thing I notice here is that the first equation and the second equation are pretty similar. And in fact, if I manipulate this second one just a little bit, I could say this is the same thing as e to the t quantity squared, because I know that when I have a base raised to a power and the whole thing is raised to another power, the powers would just multiply. But doing that allows me to say that, hey, this e to the t, that's x. So it must be the case that y equals x squared. Okay. Now, if you didn't notice that right off the bat, you could still use the same strat, because I mean that was kind of a see it or don't kind of thing. But we could still use the same strategy of solving for t. So we could have said, hey, or x equals e to the t. To solve for t, since t is up in a power, that tells me that to solve for it I would need to use a log. So I would apply a natural log to both sides. Natural log of e to the t is just t. So natural log of x is t. And then I could plug that in for t there. And that would give me y equals e to the 2 natural log x. Okay. And you know what? I could use the properties of logs to say that 2 could come up here. So that's y equals e to the natural log of x squared. But then once I move that 2 up, now the natural log and the e are acting in sequence, and they cancel each other, and I get y equals x squared. So either of those would be a correct way to do it. Obviously this one was a little slicker, but this one kind of fits with the idea of pick one equation, solve it for the parameter, and then plug into the other. We can always fall back on that. Either way though, there's something else subtle that I need to catch. X equals e to the t. E to the t, if this is the t-axis, and in this case, since x is the output variable, x would have to be the vertical axis. Okay, x equals e to the t looks like this. Okay, it increases without bound going to the right, but going to the left it follows the horizontal axis asymptotically, which means x never drops below 0. In fact, it never even gets down to 0. X can only be positive numbers. That domain restriction needs to carry down. Otherwise this isn't really equivalent to my original parametric equations, because that domain restriction would clearly prevent me from having any positive x values up here. So I need to say, comma, x is greater than 0. Either way I do this. Okay, because when I graph my parametric equations, so this is kind of an or, when I graph my parametric equations, I'm not going to get a whole parabola. I'm actually only going to get a half parabola. Okay, and that's significant because the problem also asked me to sketch my graph. Well, I know how to sketch y equals x squared, just a standard parabola. Okay, when x is 1, y is 1. When x is 2, y is 4. Okay. But normally I would go ahead and sketch the other side, but in this case I don't want to sketch the other side because the other side isn't actually part of the graph of those parametric equations. In fact, not even the vertex is. X has to be strictly greater than 0. Let's jump over to Desmos just to kind of get a visual check on this one. There we go. Clicky, clicky. Alright, let me first put in my parametric equations. E to the t, comma, e to the 2t. Apparently I can't type a t today. Alright, now there's really no reason why t should be restricted from 0 to 1. They didn't give us any domain restrictions, so let's let t go from like -10 to 10. Okay, and notice even when we include a bunch of negative values for t, we never get the left-hand side of our parabola. Okay, because no matter how small we make t, no matter how negative we make it, e to the -10 is still positive. It's a very small number, but it's not negative. That means my x values can never make it, they can never make it quite even onto the y-axis, let alone left of it. Alright, looks good. Now, if I wanted to graph my standard equation, I could type in y equals x squared, but notice that it defaults. Okay, it defaults to assuming that I want the whole thing, but to really be equivalent, I need to put in my domain restriction. So I would say x greater than 0. Okay, in Desmos, rather than doing comma x greater than 0, you put the x greater than 0 in these braces. Okay, and that's how you tell Desmos you're doing a domain restriction. And now it matches up perfectly with what we had up here. Alright, let's see what else is on our outline here. We did a couple problems out of the book. Okay. At this point, we've really pretty much covered everything there is to know about parameterizing functions, really. I mean, for the most part, all the big ideas we've covered. It's just not that hard to parameterize a function. You know, if your rectangular equation has the form y equals some formula of x, then pretty much as soon as you decide how to parameterize x, the equation decides for you how to parameterize y. However, there are some types of curves that aren't really functions. They're rectangular equations, their standard equations are not solved for y. Okay, circles are a good example of that. So it might seem like it would be hard to parameterize circles, but actually we have something that's just right for this. So recall that on the unit circle, if we measure the angle theta from the positive x-axis to the line connecting a point on the circle to the origin. So you know what, let me pause right there and actually draw that. I think that would be worth having a quick look at. Alright, so here's the drawing for what I'm talking about. Unit circle, a circle of radius 1 centered at the origin. Okay, if we measure an angle between the positive x-axis and the line that connects the origin up to some point xy on the unit circle, okay, we could call that angle theta. Then by definition, the x-coordinate is the cosine of theta and the y-coordinate is the sine of theta. Okay, by definition. Okay, by virtue of the fact that cosine of theta, well, I don't even want to say more about it than that, because that's really where sine and cosine come from. They were invented by the ancient Greeks to study circular arcs for the purpose of doing astronomical calculation. So really, I mean, this is the origin of sine and cosine. They were invented for this purpose. Okay. Now later, much later, we figured out how to actually compute them accurately using power series. The Greeks, I think, had to rely on triangles, as in actually drawing out triangles and taking measurements and doing division, and they probably never had more than 1 or 2 decimal places of accuracy. Okay, if you want more than that, you've really got to start getting some calculus involved. And while there was some calculus in ancient Greece, they didn't yet really know how to use it for this purpose. They knew how to compute integrals. Strangely enough, that was, as far as we know, that was the first calculus anyone ever really figured out. Archimedes used integrals to find formulas for geometric figures. It wasn't even new in his time. He was building on a method called, the Greeks called it the method of exhaustion. It was really just what we now call taking a limit. And it was something that even was went back even further than him. Alright, well, anyway, here's my point. Sine and cosine, by virtue of how they're defined, automatically give us a parameterization for the unit circle. X equals cosine theta, y equals sine theta, constitutes a set of parametric equations that describes the unit circle. And here the parameter isn't time, it's the angle variable theta. Okay, and this is pretty common too. And now we're kind of starting to get into why this topic is so important to Calculus 3. In Calculus 3, we work a lot with surfaces that are built on these kind of curves that aren't really functions. And a lot of times when you're working with surfaces, it's easier to describe them parametrically than it is with a standard equation. Not always, but a lot of times. There's advantages of that because parameterization gives you so much more control over each variable. So anyway, we have to be able to parameterize things like circles for Calc 3, and the unit circle is super easy to parameterize. Alright, let's hop back over to our outline. Yeah. Boom. So we just discussed that. Here we go. Alright, so here's something you learned about if you took college algebra or pre-calculus. We cover it in there. Otherwise, you probably learned this in like a high school algebra or high school pre-calculus course. Okay, it's a formula for the standard equation of a circle with a center at the point h comma k and a radius of r. So in general, the equation for that circle would be x minus h squared plus y minus k squared equals r squared. Okay, so let's apply that to the unit circle. So that formula was x minus h squared plus y minus k squared equals r squared. But for the unit circle, the center is 0, 0. So that's my h and my k. And the radius is 1. So in my unit circle, that's x minus 0 squared plus y minus 0 squared equals 1 squared. And if I simplify that, that's just x squared plus y squared equals 1. And that probably looks familiar, even if this wasn't looking familiar a minute ago. You probably remember seeing the equation of the unit circle written down as x squared plus y squared equals 1. That's the standard equation. These are the parametric equations. Okay. Now, we know that the parametric equations need to be algebraically equivalent to the standard equation. So in particular, it should be the case that if I plug cosine theta in for x and sine theta in for y, I should get a true statement. So let me see, cosine theta squared plus sine theta squared equals 1. Well, yes, that's a trig identity. Okay, we called that a Pythagorean trig identity. That was like the first Pythagorean trig identity. So maybe I'll call it Pythagorean trig identity numero uno. Boom. Number 1. Okay, yeah, this is definitely a true statement. And it darn well better be. Otherwise, we've messed something up. Okay, so it's kind of a nice check, but it's more than just a nice check. The fact that when we plug the parametric equations into the standard equations, we get a trig identity, can actually be used to help us figure out what the parametric equations should be in other cases. So we're going to build on that idea in a little bit. But first, first, well, I mean, actually, we're going to start building on almost right away. Okay. Well, anyway, let's move on. Okay, we want to now kind of do a little bit more with parameterizing the unit circle. Let's hop back and look at our outline. Okay, part B. Find an alternate parameterization of the unit circle that starts at the top of the circle. You know what? Let's go to Desmos and see what our current one does, and then that might give us some idea as to how to alter it. Okay, so to put in my parametric equations, I want to do cosine of, now in Desmos, if you just spell the word theta, T-H-E-T-A, it knows what you want. So cosine of theta, comma, sine of T-H-E-T-A. Okay. Unfortunately, it doesn't seem to know that theta is a parameter. Well, that's okay. We'll just change it to t. Okay. Well, you know what? I can see it starting to draw my unit circle here. Okay, but since it defaults to only letting t go from 0 to 1, it basically just drew a 1 radian, an arc corresponding to 1 radian. To get all the way around the unit circle, I need 2 pi radians. So let's let t go from 0 to 2 pi. If you just type pi, it knows you mean pi. Alright, that gave me my unit circle. Now let's do this. Let's do cosine of k, sine of k. Okay, this should give me the same thing, but it'll give me a little bit of control over it. I can say, alright, we want k to go from 0 to 2 pi in small steps. So like steps of, let's do 2 pi over 100. Alright, so here's k equals 0. Since we let k just take over the role of t, this would correspond to t equals 0. So I can see that in this specific parameterization of the unit circle, when t is 0, I start out at the point 1 comma 0 on the right side of the circle. Now, as I start running through the parameterization, okay, it is going counterclockwise initially. I probably shouldn't have just let that go. Here, let's run through it. Here's one time through. As t goes from 0 to 2 pi, we move counterclockwise around the circle, starting at the point 1 comma 0 and ending at the point 1 comma 0. Now, our task in part B is to change my parameterization so that rather than starting here, I start up here at the point 0 comma 1. Okay, basically, I want to make it so that when t is 0, my angle is pi over 2. So what I'm going to do is I'm just going to tack a plus pi over 2 right onto my t there. Okay, now as you can see, that generates the same circle. Okay, but it makes it so that when t is 0, the angle going into sine and cosine is pi over 2. So this time, instead of my parameterization starting at the right hand side of the circle, should be starting at the top. Let's alter this to match. Alright, so start over at k equals 0. I can see my little green dot is, yep, at the top of the circle. And then as I let k go from 0 to 2 pi, I still go counterclockwise all the way around the circle, and I end where I stop. Okay, so that's one modification to the parameterization, okay, which is a useful modification. Sometimes I need to start in a different place. Let's talk about some other modifications. That was part B. So you know what, maybe it would be good for me to actually write down what we did. Okay, let's write down what we did here in part B. We let x be the cosine not just of t, but of t plus pi over 2, and y be the sine of t plus pi over 2. That gave us a different starting point. Now, what does the outline ask for in part C? Find an alternative parameterization of the unit circle that is oriented clockwise. So both of the ones we've done so far were oriented counterclockwise. How do I make it so that it runs to the right instead of to the left? Well, when we're talking about angles in the coordinate plane, we associate positive angles with going counterclockwise and negative angles with going clockwise. So let's do this. Let's put a negative sign right on the t. And I won't make any other change. I could leave the pi over 2 there or not. Okay, but by putting a negative on the t, what'll happen is then as t goes from 0 to 2 pi, this angle here will actually be decreasing, which means that instead of going counterclockwise, we'll go clockwise. At least that's the theory. Let's check it out. Negative t, negative t. Well, that doesn't seem to have changed the graph at all. That's good. We've still got our unit circle here. Let's reset this thing. Alright, because I've still got that plus pi over 2, we're still starting up here at the top. But now watch what happens as k, which is really t, starts moving from 0 to 2 pi. Hey, we're going clockwise instead of counterclockwise. Exactly what we wanted. We reversed the orientation. So if I were drawing this on paper, which I can do, in fact, let's do that. If I was drawing this on paper, then here's my little unit circle. In this one, I would draw an arrow showing that I'm going clockwise. Up here, if I were drawing it, I would draw an arrow that shows I'm going counterclockwise. That gives me my orientation. Alright, back to the outline. What else do we want to try to do? Find an alternative parameterization of the unit circle that traverses the entire unit circle as theta goes from 0 to pi. Theta goes from 0 to pi. So basically I want to go around the circle twice as fast, half as much time. Okay, in this case, if theta is, if we're associating it with time, we're going around the circle in 6 pi seconds. I mean 2 pi seconds, which is about 6. But let's cut that in half. We'll go twice as fast. How do I go twice as fast? Well, should be the case that if I put a 2 on my t, then for every increase of 1 in t, I would get twice as much increase on my angle. So that should do it. Now, leaving this other stuff here will still make it so that I'll start at the top and I'll go clockwise. I could take the negative or the pi over 2 off if I wanted. Well, let's see if that does it. 2. Oh, that's kind of neat. Gives me something other than the unit circle, but alright, I put my 2 on the other one, I've got my unit circle back. Alright, let's reset this guy and put our 2's in here. Alright, and let's say that we only want to let k go from 0 to pi. Alright, k is only going to go from 0 to pi. Will we make it all the way around the circle? Looking good. Yep, that did it. Alright, so to make it go twice as fast, we just basically needed to put a 2 in front of the t. Worked well. Alright. Well, what else was on my outline there? Part E. Find the standard equation for a circle centered at the origin, but with a radius of 4, and then find parametric equations which satisfy that standard equation for all values of theta. Alrighty, well, let's do that then. Part E. Alright, so remember, here is our template for creating a standard equation of a circle. Okay, it's x minus h squared plus y minus k squared equals r squared, where h and k represent the coordinates of the center. Now in this problem, we're keeping the center at the origin, so it's going to be x minus 0 squared plus y minus 0 squared, but we're stretching the radius from 1 out to 4, so when I simplify it, I'm going to have x squared plus y squared equals 16. Now, remember what I was saying earlier about we're going to use our knowledge of trig identities to help us figure out what the parametric equations should be. Okay, I can see here that if I stick with, I know this doesn't work because this was the parameterization of the unit circle, and now we're no longer looking at a unit circle. Our radius is too big. But I can see why they wouldn't work. They wouldn't work because if I plug these into the left-hand side, I would get cosine squared plus sine squared, which is 1, not 16. So these clearly aren't going to satisfy this equation. Okay, but I can make a pretty straightforward adjustment here. Okay, since everything that's on this side is going to get squared, if I put a 4 here and a 4 there, then I'm going to wind up with a 4 squared in both terms. Okay, and if I factor that 4 squared out, what's left behind would be the cosine squared plus sine squared, which is 1, and then I'll be in business. So let's just check. Okay, this is our standard equation, and these are our parametric equations, but they need to be algebraically equivalent. So let's see. If I take 4 cosine theta and drop it in for x, it gets squared, and 4 sine theta and drop that in for y, it gets squared. And so the question is, does that make the left-hand side equal 16? Well, that's 16 cosine squared theta plus 16 sine squared theta. And I think you can see where this is going. We factor out the 16, and we're left with cosine squared theta plus sine squared theta. But what's in the parentheses here equals 1. So yeah, I get 16 equals 16. And that affirms that this parametric representation should be equivalent to this standard representation. Let's check that out in Desmos. Alright, get rid of all that. Alright, so here was our standard representation. X squared plus y squared equals 16. I see nothing. Well, that's because I zoomed in too much. Notice that my x and y axes don't go out far enough. Let's zoom back out. Ah, yes. Now I can see that I have a circle centered at the origin with a radius of 4. Okay, so we got our standard equation right. Check. Now let's put in our parametric equations. So for x, it's 4 cosine of t. And for y, it's 4 sine of t. Okay, and you can see it drew in, because we're using red on this one, it drew in a part of the circle. It didn't draw in all of it because t defaulted to 0 to 1. But if I change the upper bound for t to be 2 pi, now the red covers the entire circle. Okay, and the parameterization, what was that? The parameterization matches the standard equation just right. All right. Well, let's go over and let me see. That was part E. Okay, we did all that. Part F. Find the standard equation for a circle centered at 3, negative 2 with a radius of 4, and then find the parametric equations which satisfy the standard equation for all values of theta. So pretty much same deal, but we're moving the center of the circle. Alright, so since I'm building a standard equation, I'm going to come back to this x minus h squared plus y minus k squared equals r squared. My center, my h comma k, was given to be, I forgot already, was it 3, negative 2? Yeah, 3, negative 2. My r is still 4. So when I plug this stuff in, I get x minus 3 squared. Now it's y minus negative 2, so it'd be y plus 2 squared equals 4 squared, which is 16. Alright, so there's my standard equation. That's part of what we were asked to do. But now I need parametric equations. Okay, so I'm going to start with what I had before. I know that to get my radius out to 4, I needed to put 4's in front of the cosine and sine. But how do I adjust for this 3 and this 2? Well, basically I want the 3 and the 2 to cancel out when I plug in the parametric equations, because I want to get back to a sine squared plus a cosine squared. So here's the adjustment that I'm going to make it so that these parametric equations will satisfy this standard equation. I'm going to tuck a plus 3 onto the end, I guess tack a plus 3 onto the end of my x equation, and a minus 2 onto the end of my y equation. This should give me my parametric form. Okay, let's check that. Alright, so I'm going to take my standard form and I'm going to plug in this thing here for x. So instead of having x minus 3, I'm going to have 4 cosine of t plus 3 minus 3 squared plus, and then instead of having y minus 3, y plus 2, I'm going to have 4 sine t minus 2. All of that is y, so there's still a plus 2 here. And then does that equal 16? Okay. Well, you can see that the effect of adding this plus 3 cancels that minus 3, and this minus 2 cancels that plus 2, and then I'm just going to be back to 16 cosine squared t plus 16 sine squared t, and we already know that that will in fact equal 16. Okay. Now, I want you to kind of notice this. When the center is at 3 comma negative 2, the thing you add on to the cosine and the x part of the parametric equations is just the x coordinate of the center. And the thing that you tack on to the y equation in the parametric equations is the y coordinate of the center. Okay? If the center is 3 negative 2, then you add 3 to the x part and you subtract 2 on the y part. Okay? In the standard form of the equation, it's actually kind of backwards. You subtract 3 and you add 2. And it's because you were subtracting in the first place. Okay, but in some ways the parametric form is a little more intuitive than the standard form because the signs match up perfectly with the signs of the center. Okay, and this is how it would always work. Anytime you want to parameterize a circle, start with cosine for x, sine for y. Put whatever the radius is, not the square of the radius, but just whatever the radius is, put that in front of x and y, and then tack on the coordinates of the center to the ends of x and y, and you've got your parameterization. Okay, it's really in some ways kind of easier than the standard form. Although I don't think the standard form's hard either. You guys all did that back in college algebra or wherever you learned circles for the first time. Let's just stick that into Desmos and make sure that all fits the way we expect it to. Okay, yeah, let's just start from scratch. Alright, so what do we have? We had x minus 3 squared plus y plus 2 squared equals 16. Alright, so there's our circle with radius 4 that's centered at, you know what, let me actually plot in the point 3, negative 2, just so I can kind of eyeball it and see that, yeah, that looks like that's the center. Okay, 3, negative 2 is at the center. The radius is still 4. Yeah, because we're going from 3 over to like 7 there. Now, let's check out our parametric form. For x, we had 4 cosine of t plus 3. And for y, we had 4 sine of t minus 2. And again, we only get part of the circle. But if I replace that 1 with a 2 pi, now I get the whole circle. That was me clapping. A satisfied, like dusting your hands kind of clap. Yeah, that worked out pretty nice. Well, we've covered a lot of ground, but there is just a little bit more I want to go over in this. This is kind of a big introductory section. But there's just a lot of good stuff to talk about here. Stuff that's worth spending a little time on. Alright, let's see what's next on our outline. Alright, click, click, click. Oops, I went too far. Alright, discussion point. If a circle is distorted so that the horizontal radius is different than the vertical radius, well, then I guess your circle becomes more of an oval. But we actually have more of a mathy word for it. We call it an ellipse. Section 7.5, which will actually be the last section we cover, goes into depth on ellipses and other types of curves that are called conic sections. Okay? Here, we're really just going to introduce them enough to talk about how to parameterize them. Very important notion for Calc 3. So, more in-depth treatment on ellipses is coming up, but for now, let's talk about how to parameterize them. Alright, so find parametric equations for an ellipse centered at the origin with a horizontal radius of 5 and a vertical radius of 3. Okay, check your answer with Desmos. Well, I will do that. Alright, so starting over a new part A. Okay, ellipses are actually even pretty easy to handle with parametric form, which is why we're actually going to see them in parametric form before we see them in standard form. Okay, they're pretty easy to build by just thinking of them as distorted circles. Okay, I know that if I want to build a set of parametric equations for a circle, I'm going to use a cosine of t and a sine of t, and I would put the radius of the circle in front of both of them. But in this case, I want to have a different horizontal radius than I do vertical radius. So if I just put the desired horizontal radius in front of the cosine and the desired vertical radius in front of the sine, that should get it done. And as long as I don't add or subtract anything back there, that should put my center right at the origin. So let's go into Desmos and see if that does what we think it does. Okay, boom, boom, boom. Alright, so we're going to have a 5 cosine of t, and then a 3 sine of t. Okay, and again we want t to go from 0 to 2 pi if we want to go all the way around, and there is our ellipse. Okay, it's just a circle where basically we stretch the horizontal radius to be bigger than the vertical radius. It could be the other way too. I mean, the vertical radius could be bigger than the horizontal. We would still call that an ellipse. The point is, parametrically, ellipses are not at all hard to understand. You can very much just understand them as distorted circles. We'll approach them from another thought process later on. But for now, let's go on to part B. Part B, find a standard equation that is satisfied by the equations in part A. Well, here's how I'm going to get there. If I take my x, which is my 5 cosine of t, and I take my y, which is my 3 sine of t, and I square both of those, then I'm going to wind up with a 25 in front of the cosine squared and a 9 in front of the sine squared. And that's no good because it screws with my trig identity. Okay, for my trig identity to work, I pretty much need to have the same thing in front of both of them, because then I can factor that thing out. Okay, here's how I'm going to get around that. Okay, I'm basically going to toss something in that gets rid of those coefficients. 5 squared is 25, so I'm going to divide the first one by 25. 3 squared is 9, so I'll divide the second one by 9. Now when I do that, I'm just going to wind up with cosine squared plus sine squared, so that should equal 1. So there's an equation that should be satisfied with having these two parametric equations plugged in for x and y. So if I switch this to an x and this to a y, that should give me a standard equation for my ellipse, because I now have an equation that's satisfied when these things here are plugged in for x and y. Let's go over to Desmos and see if that looks right. Also, I need to remember to turn on my screen capture so you can see what I'm doing in Desmos. Alright, so let's try this out. We've got an x squared, and we're going to divide that by 25, and we're going to tack on a y squared. We're going to divide that by 9, and we're going to set it all equal to 1. Aha, and it gives me a red curve that perfectly overlaid the black curve that was already there. Okay, so yes, we successfully created a standard equation that generates the same curve as my two parametric equations, that curve being our ellipse. Excelente. Alright, that's part A down, part B down. How about part C? Find parametric equations for an ellipse centered at -2, 7 with a horizontal radius of 2 and a vertical radius of 4. Let me read all that again before I flip over to the paper. We want parametric equations for an ellipse centered at -2, 7. So we're going to have to be tacking some stuff onto the ends, with a horizontal radius of 2 and a vertical radius of 4. Okie dokie. So, to build my parametric equations, that is what it asked for, right? Parametric equations? Yes. Since an ellipse is just a distorted circle, I'm still going to start with cosine for the x and sine for the y. But I want my horizontal radius to be 2, so I'll put a 2 as a multiplier on the cosine. I want my vertical radius to be 4, so I'll put a 4 as a multiplier on the sine. Now, our center was at -2, 7, so I'll put a -2 at the end of the x equation, subtract 2, and plus 7 at the end of the y equation. This is one of my favorite things about parametric equations. When you add and subtract to get shifts, they're not backwards like they are with standard equations. That's something that I think is, I mean, you get used to it, but it kind of messes with you in standard equations. Okay, you want to shift to the right, you got to add. You want to shift to the left, you got to subtract. And it's only backwards for the horizontal ones because the vertical ones aren't in the right place, and that's even more confusing. But with parametric, you want to shift to the left, you subtract. You want to shift up, you add. Nice and easy to remember, not backwards. But let's make sure it looks right over here in Desmos. Okay, so I think I'll just alter this. 2 cosine minus 2 and 3 sine plus 7. Oops, 7. No, 7. There we go. Okay, so there's my ellipse that's centered at -2, 7. Looks good. Okay, in fact, let's put in -2, 7. Let's just put that point in so that, yeah, we can kind of visually confirm that, yep, looks like that's right in the middle of the ellipse. And it's got a horizontal radius of 2 and a vertical radius of 4. It looks good. Now, I'm guessing that part D on my outline was find the standard equation. Okay, so to find the standard equation, so remember in the standard equation, stuff's kind of backwards. In the standard equation, we subtract from x, so it'd be x minus -2. That would be x plus 2. So we're doing part D over here. X plus 2 squared. But remember, we also have to divide by the square of this horizontal radius in an ellipse. Okay, and let me see. Since the center has a y coordinate of 7, I need a y minus 7 squared. So both of those are kind of backwards from the signs they have in the actual coordinates of the center. And since my vertical radius is 4, I need a 4 squared down here, and then that'll all equal 1. Okay, so that should be the standard equation for my ellipse. Let's just check that in Desmos real quick. Let's just get rid of that and start over. Alright, so what do we got? We got an x plus 2 squared divided by the horizontal radius squared. 2 squared is 4, plus y minus 7. That 7 is the y coordinate of the center, squared, divided by the vertical radius squared. Now I know I'm kind of taking a long time on 7.1 here, but the good news is we'll have kind of a leg up when we get to section 7.5, because we'll already have kind of been introduced to standard equations of conics. Alright, when I put in the 1, I should get, well, something's wrong there. Oh, you know what's wrong? It was actually up here. I put a 3 where I was supposed to have a 4. Alright, now they match. Perfect, perfect, perfect. Alright, well, that looks good. So we must be getting very close to the end, but I think we have just maybe one more curve type to talk about. So, coming back to my outline, so what page are we even on here? We're on page 5. Yeah, this is kind of a long outline. But this is a big topic. Like I say, this is going to be pretty fundamental in Calc 3, so it's worth it to take our time and develop it well. Alright, so what are we going to do here? We're going to alter the equation of the unit circle by just a very small thing. We're going to take this plus that's in the middle of the equation of the unit circle, and we're going to turn it into a minus, and that gives us a hyperbola, which is a curve with 2 branches. Okay, a hyperbola is another type of conic section. Okay, the conic sections are ellipses, hyperbolas, circles, and also parabolas count. Those are all conic sections. Okay, we'll be studying all of those in section 7.5. Now you're probably thinking, gosh, I already know a lot about parabolas, and you do. But when we study them as conic sections, there's some special attributes that we draw out. Okay, but for now, we're going to talk about hyperbolas. And here's our first example. X squared minus y squared equals 1. So, first things first, we're just going to have a look at this thing. We're going to put that standard equation into Desmos. Alright, let's get rid of all this stuff. X squared minus y squared equals 1. So as we mentioned, there's 2 branches. Okay, they both kind of look like boomerangs to me. Okay, they're both curving here near the origin, but then they really straighten out. Okay, once you get very far away from the origin, these branches are more or less straight lines. They're not exactly straight lines, but they're following closer and closer to straight lines. Okay, some asymptotes. And we'll learn about that in section 7.5. But for right now, how would we parameterize something like this? That's going to be part B. Parameterize this hyperbola by thinking of 2 trigonometric equations that satisfy this standard equation and check with Desmos. So what does that mean? Well, for the unit circle, the standard equation was x squared plus y squared equals 1, and we kind of matched that up with one of our Pythagorean trig identities, which was cosine squared theta plus sine squared theta equals 1, and we said, hey, if we let x be cosine and y be sine, that'll give us a parameterization that satisfies this equation. But now here for our not a hyperbola, it's a hyperbola. Although that's kind of fun to say. I better not say it again, I might keep saying it. Hyperbola. The equation is not x squared plus y squared, but x squared minus y squared equals 1. Okay, our Pythagorean trig identity using sine and cosine is not going to match up with that. But we know some other Pythagorean trig identities. Okay, another Pythagorean trig identity we know is if you divide everything in this equation by cosine squared theta, you would get 1 plus tangent squared theta equals secant squared theta. Now, that doesn't match exactly, but if I rearrange it, if I move the tangent over, then I would get, I'm gonna switch sides, but secant squared minus tangent squared equals 1. That does match up. So that suggests that if we let x be secant of, we'll use t, since Desmos likes that one better, but it is okay to use theta as a parameter. If we let x be secant t and y be tangent t, this parameterization based on that trig identity should satisfy the standard equation. So these parametric equations should generate the same curve. Let's see if they do. Alright, so for the x coordinate, we're going to put in secant of t, and for the y coordinate, we're going to put in tangent of t. And you can see that that graphed just a little piece of our hyperbola over here on the right side because t defaulted to be 0 to 1. Let me see, with circles we were able to get the whole thing. Circles and ellipses, we could get the whole thing by letting t go from 0 to 2 pi. Well, that did it, didn't it? Okay. Yeah, that took, well, 2 pi is enough to take both secant and tangent all the way through their periods. Okay. In fact, tangent, the period is just pi. I wonder if pi is enough. No, it doesn't do it. But notice, if we go from 0 to pi, all the y values are covered. Okay, they're covered once. Okay, because tangent has been taken all the way through its period once. Okay. However, since secant hasn't completed the second half of its period, we haven't gotten the second half of our two curves. That's kind of interesting. Okay, it looks like we need 0 to 2 pi. Now, of course, if we went more than that, we would just retrace them. Okay, and actually that's kind of, I mean, that would be like going around the circle more than once. That's kind of interesting too. Well, let's go back to our outline. Ooh, now this is interesting here. We parameterized our hyperbola by thinking of two trigonometric equations, but now in part C it's saying parameterize this hyperbola by thinking of two non-trigonometric equations that satisfy this standard equation. Well, do I know any non-trigonometric equations, any non-trigonometric functions where one of them squared minus the other one squared is 1? Now, I realize that might not just jump right out at you, but we have talked about two functions that are just like that. Okay, the functions that we've talked about, other than trig equations that behave that way, are hyperbolic cosine and hyperbolic sine. So recall this identity. Okay, we looked at an identity back when we introduced hyperbolic sine and cosine, or reintroduced them earlier in the course, that said, hey, if we've got hyperbolic cosine squared minus hyperbolic sine squared, that equals 1. So it seems like it ought to work just as well as secant and tangent if we parameterize this hyperbola by letting x equal hyperbolic cosine of x, not x, of t, x be hyperbolic cosine of t, and y be hyperbolic sine of t. Why did I write cosine? Well, let's try that parameterization out. Okay, so alternative parameterization. Hyperbolic cosine of t, comma, hyperbolic sine of t. Oh, I left out the h. It's like, why didn't that match? Alright, so it's drawing this one in black, I see from looking over here. Now again, that only drew a part of my hyperbola, so no big deal. Let's expand our domain for t here. Let's go up to 2 pi. Alright, that gave me more. Well, maybe I need to go higher than that for the parameterization. Let's do 4 pi. Maybe we need some negative values of t. Negative 4 pi. Alright, well now I've got the entire right-hand branch. Let's go really far. Let's do like negative 100 to 100. I'm still only getting the right branch. Well, so it's working, but it's not really giving me the whole thing. What's the deal here? You know, this is kind of a subtle thing, but here's what the deal is. The deal is hyperbolic cosine. Let's flip back over to the paper. Hyperbolic cosine of t, by definition, is 1/2 e to the t plus 1/2 e to the negative t. Okay, e to the t can never be negative. E to the negative t can never be negative. So when I add these two things together, I'm never going to get any negative values. Okay, the outputs of hyperbolic cosine are all positive. And since hyperbolic cosine is what I'm using for x, I'm only ever going to get the right-hand branch of the parabola. Which means that in some ways, this isn't as good of a parameterization as using secant and tangent, because it really can't capture the whole thing. Okay, now I could do another parameterization to get the other side. I mean, check this out. If I just put a negative in front of the hyperbolic cosine, yeah, let's do like 100 to negative 100. Okay, did that in red. That gave me the other side of the hyperbola. So I mean, I could use two parameterizations to get the two curves, the two branches of the curve. But I really can't use a single parameterization involving hyperbolic cosine and hyperbolic sine to get my hyperbola. So in some ways, not quite as good as using secant and tangent. But it does work. And a lot of times, applications with hyperbolas are only interested in one branch or the other anyway. So sometimes it's just as good to do it this way. Part of what I wanted to bring this up about is, notice how if we let x be regular cosine and y be regular sine in our parametric equations, we get a circle. But if we let x be hyperbolic cosine and y be hyperbolic sine, then instead of getting a circle, we get a hyperbola. And that's actually the origin of the names of these functions. I mean, if you think about it, those names don't even really make sense on the surface, as it's like this function is really just a couple of exponential functions added up. How is that even connected to cosine? Well, this is actually the reason. And not only is it like, how's that connected to cosine, it's also kind of like, how's that connected to hyperbolas? Why is this a hyperbolic cosine? But now you know the reason. It's because this function plus that function, which is the same thing but with a minus in the middle, together can parameterize a hyperbola. And they do it in the same way that sine and cosine parameterize a circle. So that's how they came up with the names hyperbolic cosine and hyperbolic sine. Okay, I know that's kind of a stretch, but these functions are so important that they needed to have their own names. And because parameterization is something we do so much, it kind of made sense to draw inspiration for their names from what they can parameterize easily, hyperbolas. So anyway, that's that. Let's see what else is on our outline here. Click, 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 click. Aha, a book example. And then that's it. So we'll do one example from the book, and then here's the homework problems from the book that you guys need to do. And we're nearly at the end of this recording, but one more problem. All right, we want to do problem 30 from the book. All right, so in problem 30, we're given a set of parametric equations that use hyperbolic cosine and hyperbolic sine. So apparently this is a parameterization of a hyperbola. And what are we to do? We're to convert the parametric equations of a curve into a rectangular form. No sketch is necessary. State the domain of the rectangular form. Well, since I know that they're hyperbolas, then I know I'm looking at something that's akin to that x squared minus y squared equals 1. But just like I had to adjust in the ellipse by dividing the x squared and y squared when I had coefficients here, I'm going to have to adjust in my hyperbola. So, and it's pretty much the same adjustment. Let's have a look at this. Okay, so here was my standard hyperbola, or my simple one. X squared minus y squared equals 1. I parameterize that with x equals hyperbolic cosine of t and y equals hyperbolic sine of t. But now they've given me this parameterization where broke my lead again. Maybe I need to drink a little less coffee. Nah, I can give up the leads. Who cares? Who would give up coffee? Someone with more discipline than me, that's who. Why, I gotta look at it again. It was x equals 2 hyperbolic cosine t and y equals 4 hyperbolic sine t. Okay, so I'm going to use this as my template. Okay, but since we've got this 2 and the 4 there, when we plug this in for x, the 2 would get squared and it would produce a 4. And I'm going to offset that by putting a 4 under the x squared. So I'm going to do an x squared over 4 minus a y squared over a 16 to offset this 4 when it gets squared when we plug this business in for y. Okay, and then the equation should still work. So let's just go over to Desmos and see if this standard equation here gives me the same curve as these two parametric equations. And we'll do it knowing that the parametric equations will only produce one branch. The standard equation should produce both branches. Okay. And you know what? That we were actually told to state the domain. Let me look back at the book real quick. What did it say here? It said state the domain of the rectangular form. Okay, so actually, one more little thing we need to do here. We need to say that x is greater than or equal to 2 because hyperbolic cosine is always at least 1. Okay, we saw that before. I mean, basically e to the t plus e to the negative t got to be at least this has got to be at least this sum e to the t plus e to the negative t is at least is at least 2 times a half is 1. Anyway, the domain of hyperbolic cosine starts at 1, so the domain of 2 times hyperbolic cosine starts at 2. So actually, we have this domain restriction on the rectangular equation, and if I type that into Desmos, then the rectangular equation will match the parametric, and we'll just get the right-hand side. All right, let's start with the parametric. So x equals 2 hyperbolic cosine of t, and y equals 4 hyperbolic sine of t. And we'll go from negative 10 to 10. Okay, and we're getting the right-hand branch of a hyperbola. That's what we expect. Now let's put in our x squared divided by 4 minus y squared divided by 16 equals 1. Now that gave me both branches, but if I go over here and put in some braces and say, hey, x has got to be greater than. Now watch that. I typed greater than, but now I'm going to type equals, and it knows I mean greater than or equal to. X is greater than or equal to 2. That puts my domain restriction on the standard curve, and it makes the green curve match up exactly with the blue curve. And that's what we needed. So yeah, whenever we convert from parametric form to rectangular form, we've got to think about domain restrictions that were caused by the parametric equations, and if need be, we need to explicitly state them with the standard form. All right, well, we are now at the end of our recording for section 7.1, last chapter, home stretch. As always, I want to encourage you guys, if you have questions about anything, get in touch with me. We'll set up a Zoom session and we'll go over all your questions. And also let me encourage you to keep on keeping on. Keep up the faith, my friends. I know it seems like kind of a long slog to get through this extended quarantine. It may be still going on for quite some time, but it is making a difference. It is saving people's lives by doing this. So think of that every time you think of how inconvenient it is to not be able to go out and do fun stuff with your friends. I certainly miss seeing my friends face to face, and I definitely miss seeing you guys face to face. But it is worthwhile. We will get to see, I may not get to see you guys again, but you will get to see your friends and future teachers. So take care, stay strong, stay healthy.